Okay, welcome back here. We are picking back up in section 3.2. We just talked about coefficient of variation. So we're jumping into this example, which is two data sets. Data set A has a standard deviation of 8.75 and a mean of 126.08. Data set B has standard deviation 9.3 and mean of 99.22. So we're going to ask the question, which data set has more variability? So we're going to calculate the coefficient of variation for A and the coefficient of variation for B. So for A, this is 8.75 over 126.08 times 100. And this gives us 6.94, forgot the 9, and this is a percent. And the coefficient of variation for set B is 9.3 over 99.22 times 100, and this is 9.37, and this is percentage. So what this percentage tells us is the amount of the mean that the standard deviation takes up. And so what we mean by that is the more percentage that your coefficient of variation is, means the higher variability. It means that your standard deviation is larger. So if your mean is here, a smaller standard deviation, a smaller percentage of that mean keeps things close to the mean. A higher percentage pushes it back out and causes high variance in your data. So since the standard deviation of data set B is a larger percentage of the mean, it means B is more varied, or i.e. is more spread out. So remember, all of these measures that we're calculating in this section are measures of dispersion. They're measures of spread. They tell us how far they spread out. So a higher coefficient of variation means a more spread out data set. So moving on here, we have our final calculation, our final term, not final term, but final calculation, that's variance. So variance is just the square of the standard deviation. So for population variance, it's sigma squared. I know, very creative. And all it is the formula for standard deviation without the square root. Same thing for sample variance. It's S squared, the formula for standard deviation without the square root. So variance is actually a more common, a more popular measure of dispersion among statisticians to a degree, only because it's slightly easier to calculate than the standard deviation, because you don't have to square root anything at the end. So we're going to calculate the sample variance of our number, and we are going to do it on the calculator. So the first thing we're going to do, these are hours per week a sample of student workers are scheduled at their tutoring jobs. So the first thing we're going to do is edit our first list. We're going to enter 6, 5, 4, 3, 5, 9, 8, 7. Make sure there's nothing else. Looks good. Quit, stat, calculate, one var stats, and hit enter. So notice there's nowhere on here that has the variance. They give us standard deviation. So we are calculating sample. We know because it tells us to calculate sample. So S is 2.031009601. Now you're probably saying, why are you including so many decimals? Well, the reason is when you're doing variance without doing it directly by calculating it directly, and you're using this, this is a square root. So that means we need to be as accurate as possible, so we're going to include all the decimals and just square that number, 2.031009601 squared. 4.124999999, so that means s squared is 4.125, rounding that up. So we have our variance calculated using standard deviation as the guide using the calculator. So we do have one remark just to keep in mind, and that is variance is going to be very common in future chapters. So variance will be used for many concepts. In future chapters. So variance, like I said, it's a more likable calculation than standard deviation because you don't have to square root anything. But with a calculator, standard deviation isn't horrible. Excuse me. So for the last couple things, the empirical rule, this is specifically for bell curves. When we talked about bell curves, they are symmetric distributions. So the empirical rule means moving out in both directions from the mean. We have about 68% of all data is within one standard deviation on either side, and so you can see that here in this diagram I've given you. So at the very, very center is the mean, mu. Going this way we have 34%. Going this way we have 34% of our data. Going out this direction, so from here to here, we have an increase, and there is, in this distance here, 95%. So that's 95% of all data is within, oh, this should say 2. I think I just copied and pasted 2 standard deviations. So from here to here is 95% of all your data. And then out here is the outlier. And here we can't even guarantee everything. So that's from here to all the way to here. And going back this way as well to there. We can't even guarantee that we can hit everything within 3 standard deviations. And so it's 99.7% of all data. So anything outside of 3 standard deviations is a true outlier. And again, this should be 3 standard deviations. It's a true outlier if you are outside of this range. And you typically don't see data that far out, right? 0.3% of your data. So the empirical rule is really important for bell curves, obviously. It tells you where your data most likely falls. Most of it's hitting right in 1 standard deviation, which makes sense. It's 1 standard distance unit, 1 standard mean away. So let's take a look at a little example. The distribution of birth weights is bell-shaped with a mean of 500 grams. No, this is wrong. This is a mean of 3,000 grams and standard deviation of 500 grams. Now, I believe your packets are correct. If not, that's the correction. 3,000 is the mean and 500 is the standard deviation. So what percentage of newborns weigh between 2,000 grams and 4,000 grams? So typically what we do is make a little bell curve. We put the mean right at the center, 3,000. And we do a bell. Now your bell doesn't need to be perfect. So 1 standard deviation is 500 away. Down is 2,500, up is 3,500. 2 standard deviations away, down is 2,000, up is 4,000. So we want to know what percentage of newborns weigh between 2,000 and 4,000. Well, this is 2 standard deviations, so going back to our empirical rule back here. That's 1, 2. That's our 95% rule. So the answer here is 95%. Now, that's a pretty straightforward example of using the empirical rule. For part B, they're asking us to be a little bit more tricky about things. So what percentage of newborns weigh less than 3,500 grams? So again, do the same thing, 3,000, 2, 1, 2, 2,500, 3,500, 4,000, 2,000. Oh, it was a bad bell curve. Ignore that. Your bell curves don't need to be perfect when you draw them. So we are saying here and less. What percentage? Well, the nice thing is the mean, if it's bell curved, means that from here to here, this is exactly 50%, statistically speaking. Because this splits our mean, if it's bell curve, splits our data perfectly in half. It's the exact middle. So, if this is 50%, we just need to know how much is this? Well, our chart on the other side tells us that. If it's 68% from one standard deviation left to right, that means that, as we've written here, it's 34% one standard deviation up or one standard deviation down. So right here is 34%. So that means we have 50 plus 34, or 84%, is our answer for part B. So that's an interesting use of the empirical rule. You'll have some homework problems that deal with that. So our last thing is Chebychev's theorem. So this is the same kind of thing as the empirical rule was, but it's for non-bell-shaped distributions. So all the other shapes that we talked about at the end of chapter 2 that aren't bell-shaped, that includes non-bell symmetric curves. And so the inverted shapes. So the proportion of data that lie within k standard deviations of the mean is at least 1 minus 1 over k squared for k greater than 1. Now we don't do this for k equals 1. When k equals 2 and k equals 3, just an example, Chebychev's theorem says at least 1 minus 1 over 4, 2 squared, which is 3/4 or 75% of the data is within 2 standard deviations. When k equals 3, at least 1 minus 1/9 or 8/9, which is approximately 88.9% of data is within 3 standard deviations. So you can use this to calculate higher than 1. And this gives you a way to handle non-bell-shaped curves. Now, for the most part, you have a couple questions about Chebychev's theorem in the section. We're going to be focusing primarily on bell curves for the majority of this class. So if you think, wow, this is really weird, it is really weird. We tend to, in statistics, like bell-shaped distributions because they're very well studied and well known. But this is the end of 3.2. The next video will tackle 3.3.